Density contrast interface inversion. The conventional prism-based inversion usually produce diffusive images, even though some techniques such as focusing inversion can be used to enforce a sharp boundary between different geological units. In petroleum reconnaissance using gravity method, it is of great importance to estimate the depth to basement. However, from the interpretation of conventional prism-based inversion, it is difficult to pick up the correct location of such interface due to the non-uniqueness of the inversion and the low resolution of inverted density distribution. In such environments, the density contrast between sedimentary rocks and basement is usually well known based on other information such as drilling. The gravity anomaly can be attributed to the variation of the sediment-basement interface. Based on the method introduced in Section 2, this type of models can be simulated using the column discretization or the Cauchy-type integral approach. In this subsection, we will mainly focus on the inversion of sediment-basement interface using the 3D Cauchy-type integral approach. Within the framework of this approach, we formulate the inversion with respect to the depth to basement, and the density contrast value may not necessarily be a constant. Similar to the prism-based inversion, we can formulate the inverse problem using the parametric functional introduced in 17. However, the model parameters now become as follows. Where is the depth to basement at different horizontal locations, and rho is the density contrast value between the sediment and basement. Comparing to the prism-based inversion for the density distribution, the forward modeling operator, which is related with the 3D analog of Cauchy-type integral, for density contrast surface inversion is a nonlinear operator since the gravity data does not have a simple relationship with the depth. Such inversion can be solved with the gradient-type inversion methods. The sensitivity matrix for the depth to basement and the density contrast values can be calculated by directly differentiate 14, with respect to the depth to basement and the density contrast value. In some applications, the density contrast values are usually well known based on well logging. Under this circumstance, only the depth to basement value need to be inverted and the non-uniqueness of the inversion can be reduced significantly. As an example, we consider a 3D sedimentary interface model with the vertical section shown in. We consider a constant density value for the basement rock. To be realistic, we assume that the density value for sediment increase exponentially with depth due to compaction. As a result, the density contrast value will decrease exponentially with depth and approach the basement density, which is assumed to be a constant. The synthetic gravity data is simulated on the Earth's surface and will be used for inversion. For this model, we consider that the density contrast profile with depth is already known and only invert for the depth to basement. Shows a comparison between the true model and the inverted model using the Cauchy-type integral approach. One can see that the depth to basement and the shape of the sedimentary basin is well recovered in the inversion. A vertical section, y equals 0, of the sediment interface model with exponential density contrast in vertical direction. Inversion result for the synthetic sediment basement interface model with exponential density contrast. During the inversion, we use a flat surface as the initial model and a priori model. Actually, such inversion method is robust enough and does not depend too much on the selection of initial model and a priori model. However, one can use some other initial model in order to speed up the convergence of the inversion. The famous Bugay slab formula can be used as an initial model. Where G notes the observed Bugay gravity anomaly, delta rho 0 is the density contrast value on the Earth's surface and AIS the gradient of density contrast in vertical direction. As one may note, this equation works properly for the constant density contrast or linear density contrast, but it does provide a good approximation of the depth to basement for a general case, for example, exponentially increased density contrast profile with depth.